Hello students, I am Assistant Professor Dhanashree Saban from Professor Sambhajirao Kadam, College Deur. Today we will discuss about our new syllabus NEP 2.0 of Shivaji University, BSc Part 1st, Semester 1st, Department of Mathematics, Paper 1st, Basic Algebra. In this video, we study polar and exponential form. Most people are familiar with complex numbers in the form z is equal to a plus bi. However, there are some alternate forms that are useful at times. In this section, we will look at both of those as well as a couple of a nice facts that arise from them. Geometric interpretation. Before we get into alternative forms, we should first take a very brief look at natural geometric interpretation of complex numbers, since this will lead us into our first alternate form. Consider the complex number z is equal to a plus b iota. We can think of this complex number as either the point AB in the standard Cartesian coordinate system or as the vector that starts at the point AB. An example of this is shown in figure below. In this interpretation, we call the x-axis the real axis and the y-axis imaginary axis. We often call the xy plane in this interpretation the complex plane. Let's now take a look at the first alternate form for a complex number. If we think of the non-zero complex number z is equal to a plus b iota, z is equal to a plus b iota as the point AB in the xy plane, we also know that we can represent this point by the polar coordinate r theta, where r is the distance of the point from the origin and theta is the angle in radians from the positive x-axis to the origin to the point. When working with the complex numbers, we assume that r is a positive and that theta can be any of the possible both positive and negative angles that end at the ray. Note that this means that there are literally an infinite number of choices for theta, excluded z is equal to 0, since theta is not defined for the point 0, 0. We will therefore only consider the polar form of non-zero complex numbers. We have the following conversion formulas for converting the polar coordinates r theta into the corresponding Cartesian coordinate of the point AB. A is equal to r cos theta, b is equal to r sin theta. We substitute thus into z is equal to a plus b iota and factor the r out. We arrive at the polar form of the complex number. Note as well that any two values of the argument will differ from each other by an integer multiple of a 2 pi. This makes sense when you consider the following. For a given complex number z, pick any of the possible values of the argument, say theta. If you know increase the value of theta, which is a really just increasing the angle that the point makes with the positive x-axis, you are rotating the point about the origin in a counterclockwise manner. Since it takes 2 pi radian to make one complete revolution, you will be back when you reach theta plus 2 pi and so have a new value of the. If you keep increasing the angle, you will again be back at the starting point when you reach theta plus 4 pi, which is again a new value of the argument. Continuing in this fashion, we can see that every time we reach a new value of the argument, we will simply be adding multiple of a 2 pi onto the original value of the argument. Likewise, if you start at theta and decreases the angle, you will be rotating the point about the origin in a clockwise manner and will return to your original starting point when you reach theta minus 2 pi. Continuing in this fashion, and we can again see that each new value of the argument will be found by subtracting a multiple of a 2 pi from the original value of the argument. Likewise, if you start at theta and decrease the angle, you will be rotating the point about the origin in a clockwise manner and will return to your original starting point when you reach theta minus 2 pi, continuing in this fashion. And we can again see that each new value of the argument will be found by subtracting a multiple of a 2 pi from the original value of the argument. So we can see that if theta 1 and theta 2 are two values of a argument, then for some integer k, we will have theta minus theta 2 is equal to 2 pi k. Note that we have also shown here that z is equal to r into cos theta plus iota sin theta is a parametric representation for a circle of radius r centered at the origin, and that it will trace out a complete circle in a counterclockwise direction as the angle increases from theta to theta plus 2 pi. The principal value of the argument, sometimes called the principal argument, is the unique value of the argument that is in range minus pi less than argument z less equal pi and is denoted by argument z. Note that the inequalities at either end of the ranges tell that a negative real number will have a principal value of the argument of argument z is equal to pi. Recalling that we noted above that any two values of the argument will differ from each other by multiple of 2 pi leads us to the following fact: argument z is equal to argument z plus 2 pi n, where n is equal to 0 plus minus 1 plus minus 2 up to so on. Now that we have discussed the polar form of the complex number, we can introduce the second alternate form of a complex number. First, we will need Euler's formula. E iota theta is equal to cos theta plus iota sin theta. With Euler's formula, we can rewrite the polar form of a complex number into its exponential form as follows: z is equal to r e iota theta, where theta is equal to argument of a z, and so we can see that much like the polar form, there are an infinite number of possible exponential forms for a given complex number. Also, because any two arguments for a given complex number differ by an integer multiple of a 2 pi, we will sometimes write the exponential form as z is equal to re iota theta plus 2 pi n, where n is equal to 0 plus minus 1 plus minus 2 up to so on, where theta is any value of argument, although it is more often than not the principal value of the argument. To get the value of real can either use to write the exponential form, or we can take a more direct approach. Let's take the direct approach. Take the modulus of both sides follows. Modulus of z is equal to mod of real iota theta is equal to mod of r mod of cos theta plus iota sin theta, and we see that r is equal to mod of z. Next, De Moivre's theorem. De Moivre's theorem is one of the fundamental theorem of complex numbers, which is used to solve various problems of a complex number. This theorem is also widely used for solving trigonometric functions of multiple angles. De Moivre's theorem is called De Moivre's identity and De Moivre's formula. This theorem gets its name from the name of its founder, the famous mathematician D. De Moivre's theorem statement. De Moivre's theorem is a special theorem of a complex number which is used to expand the complex number raised to any integer. De Moivre's formula stated that for all real values of x, cos x plus iota sin x raised to n is equal to cos nx plus iota sin nx, where n is any integer. Here is the proof of De Moivre's theorem. Uses of De Moivre's theorem. De Moivre's theorem is used for various purposes. Some of its most important uses are finding the roots of a complex number, finding the relationship between power of trigonometric functions, and trigonometric angles. Here are some examples of a De Morgan's theorem. If z is equal to cos theta plus iota sin theta, show that zn plus 1 by zn is equal to 2 cos n theta, and zn minus 1 by zn is equal to 2 iota sin theta, sin n theta. Let we know that z is equal to cos theta plus iota sin theta by De Morgan's theorem. Zn is equal to cos theta plus iota sin theta n is equal to cos n theta plus iota sin n theta. Here we apply De Morgan's theorem formula. Therefore, z raised to n is equal to cos theta plus iota sin theta raised to n is equal to cos n theta plus iota sin theta. Here we take a reciprocal. 1 by z raised to n is equal to z raised to minus 1. Therefore, cos n theta minus iota sin theta. Therefore, we adding z raised to n plus 1 by z raised to n, we get 2 cos n theta. Similarly, we solving for zn minus 1 by zn. Here are some other examples of De Morgan's theorem. Thank you.